All right, let's talk about one of those incredibly clever, almost invisible technologies that literally keeps the Linux kernel from falling apart. It really is a true unsung hero of system stability.
I mean, have you ever stopped to think about that? It's a huge question. The kernel is changing all the time. Thousands of developers are contributing to it. And yet, this massive ecosystem of drivers and modules, it just keeps on working. How? Well, the answer lies in a very carefully managed promise.
And that promise has a name: the Application Binary Interface, or ABI. You can think of it as a contract between the kernel and all its modules. It lays out the exact rules for how they connect and communicate. The whole plug and socket analogy, it's perfect here. If the plug fits the socket just right, everything works.
And look, this is not just some minor technical detail. This is the very foundation of stability for the entire Linux world. If the kernel suddenly changes the shape of that socket without telling anyone, well, all the modules that were built for the old shape just won't fit anymore. They'll fail to load, and that can cause system instability, maybe even total chaos. So, how has Linux kept this promise for all these years?
Well, for a very long time, the kernel relied on a system that made its promise based on the source code itself.
The tool for this job was something called genksyms. You'd enable it in your kernel configuration with config mod versions. And honestly, for decades, this was just the standard way of doing things.
And here's basically how it worked. First, genksyms would go and scan the kernel's source code. From that code, it would generate a unique signature. Think of it like a fingerprint or a checksum for every single function the kernel exports from modules to use. Then, when you tried to load a module, the kernel would compare the module's signatures with its own. If they didn't match, boom, the module was rejected. Simple, right? And for a while, it was effective enough.
But as programming languages and compilers got more and more sophisticated, some really serious cracks started to show up in this whole source code-based approach.
Here's the fundamental flaw, and it's a big one. genksyms was only looking at the recipe, the source code. It had no idea what the finished cake, the actual compiled program, looked like. It had zero visibility into all the complex optimizations and transformations a modern compiler does. So it was basically just making an educated guess about the final ABI.
And that guesswork completely falls apart with languages like Rust, which, as you know, is now supported in the kernel. The way Rust is designed, its source code just doesn't have enough information to accurately predict the final ABI. The old system was it was broken. It was fundamentally incompatible with this new reality. The promise was being broken.
Which, of course, led everyone to a crucial question. We needed a new way to check the ABI, not based on the blueprint, but on the final finished building itself.
And the solution came from a really powerful, standardized format that was, in a way, hiding in plain sight: debugging information.
Meet DWARF. If the source code is a rough sketch, DWARF is the final, incredibly detailed architectural blueprint of the compiled program. It's generated by the compiler, and it describes the finished product with perfect accuracy. Every function, every data structure, every little detail of the actual ABI is right there.
So let's put these side by side, because the difference is just night and day. The old tool, genksyms, was working on source code. It was an approximation, a guess. The new tool, DWARF, works on that rich dwarf information from the final file. It is not guessing anymore. It's looking at the absolute ground truth of the ABI.
Now, it's worth pointing out that DWARF isn't the only type of debug info out there. There's also something called ORC. ORC is way simpler and faster, which makes it perfect for mission-critical things, like trying to figure out what went wrong during a system crash, right when every microsecond counts. But for this job, for getting a perfectly accurate, rich description of the ABI, DWARF is absolutely the right tool. It's all about trade-offs. Okay, so we have this powerful new tool. What does it actually let us do? Why is this such a big deal? Well, it's all about maintaining what's called a stable KABI, or kernel ABI.
And this gets us to the real-world impact. Think about the people who maintain the big Linux distributions. Red Hat, Canonical, SUSE. They are constantly needing to backport security fixes and other small updates to the kernels they ship to customers. And they have to do this without breaking the ABI, without breaking all the modules their customers are using.
This new DWARF-based system gives them something like surgical control. With a special -stable flag, they can literally tell the versioning system to ignore certain changes that don't actually break compatibility. So for example, they can add new fields to the end of a data structure, or even tweak its size for versioning.
This is absolutely crucial for them to deliver critical security updates to long-term support kernels safely and without causing a catastrophe.
So you see, this whole transition from source code guessing to dwarf-based analysis, it is so much more than a clever hack. It's a foundational shift. It's what allows the entire Linux ecosystem to evolve, to bring in new languages like Rust, and still remain incredibly stable and secure for millions of us. It truly is an invisible guardian.
And that really makes you wonder, doesn't it? As our software and our systems get exponentially more complex, what other unseen innovations are humming away in the background, just quietly keeping everything together? And what's going to be the next one we realize we absolutely can't live without?